right. Much like the vampire that I am, we have to all sit in the dark here. Can't see the outside world. No fun. No sunshine. All right. All right, so we are finishing our way through the SN1, SN2, U1E2 chapter. One of the confusing chapters that we have. Extremely nitpicky and detailed and troublesome, I guess, might be the other term. Right? The next exam is tricky, right? And it means you guys really have to be able to convince yourself about which is the major organic reaction, right? What's the major mechanism that takes place? All these kind of things that you want to say there. Okay? So make sure that you guys are starting to practice building your case, right? If you'll notice, the first thing that I do whenever I approach any of these problems, I always stop and think about what it is. As soon as don't just put pen to paper. Oh yeah, I know what it is. Yeah, okay. You skip steps, right? What does skipping steps do? Don't do it. Okay? I'm telling you guys. I'm not trying to, hit a point that I've already hit before, and I know you guys know this and all that, right? But just don't skip steps. It has to be deliberate. Okay? I know you guys just want to get it done and go through all this kind of, right? I get it, but take your time, think about what it is, build a case, then do your mechanism with it, right? That is the tricky part of this chapter, right? How much time have we spent in chapter 6 here? Has it been like 2 weeks now? Maybe more, right? Is it a big chapter in the book? Yeah? Have you guys read the book? Have you guys worked the problems in the chapter? Have you been doing it every day? Have you worked the stuff in the back of the book? Have you guys been looking up anything that might be tripping you up? Or are we just waiting until the week of the exam and say, yeah, I'll deal with it then? Just telling you guys, I want you guys to, I'm not berating anybody. My point is never to make anybody feel bad, right? I'm telling you guys how to be successful. If you don't want to listen to me, that's fine, right? I can't make you do that. But this is something that you have to do every day, right? You have to be doing this every day. Otherwise, it's not going to soak in. And if it doesn't soak in, that means you don't understand it. If you don't understand it, you're not going to get it right. I'm sorry, there's no black and white answers here. There really aren't, okay? If I could make this all black and white for you guys, I would. It'd be a little bit easier, but it's not. It's just the nature of the game. So you have to understand. Good. No. No, it sucks, Doctor. I know. Don't worry about it, okay? But the mechanisms and the steps and the ideas and the principles that we talk about in this chapter, we're going to see again in chapter 7. And we're going to see it in chapter 8. We're going to see it in chapter 9. And then we're going to see it in chapter 10. And then we're going to see it in I think chapter 11 is NMR, right? No, you're right, it's in chapter 11. And it's in chapter 12 and 13, but not 14 and 15, because that's NMR and IR. Okay, all right. So you guys have the next 7 chapters with this stuff. And then after we're done with chapters 13 and 14, which is the NMR and IR, then guess what happens? We'll see those principles again, and again, and again. This is a core set of reactions and steps that you guys will see. Got it? The idea of an SN2 reaction and paying attention to what? SN2, the first thing that should pop to mind.
Ratio of carbocations, 3 pairings.
F! Get out of my classroom, Freddie. SN2 reaction.
Oh, do you say SN2?
SN2 reactions. Sterics. Yes, but before that, sterics. Okay? Sterics. SN1 reactions. It's the first thing that should pop to mind. You got it! Right? And so if we back that idea out just a minute, right? The formation of a carbocation comes with electronics. Okay? You guys should always start your line of thinking from sterics and electronics. Where's a strong bond? Where's a weak bond? Where's my carbocation? Is this a strong base? Is this a weak base? Is it delocalized? Is it localized? Sterics is how much junk is there? Is there junk next door? Do I have a bulky base? Do I have a non-bulky base? Right? Is it a secondary leaving group? Is it primary? Is it tertiary? All these kind of things. Okay? On the next exam, I'm going to ask you to list me the reasons why this reaction happened. Okay? One of the reasons can't be because I really wanted to. Okay? I wish it was that way because then my research would be super easy. Because I just have to sit there and stare at my reaction and say, come on, I really want, right? That's not how it works. Okay? We have certain ideas and principles that make these things happen. Good. Okay. So how do we know when a more stable carbocation forms? How do we know when something's a strong base or a weak base? I know you guys know this, come on. No, not Sophia. I'm gonna start calling on people. Let's see, who's trying not to make eye contact here? That's Sophia. I know you guys know, come on, somebody tell me what makes a strong base or a weak base. Delocalization of a
Lone pair.
of a charge, right? Everything that you said was fine, but let's broaden it out, right? Delocalization of a charge. How do we stabilize or how do we delocalize charges?
With resonance.
Okay, resonance is certainly one important way. How else? Radius. The bigger the radius, the more delocalized it is, right? How else? Electronegativity. The more electronegative something is, the better it is at handling that. What else? Inductive effects. That's inductive effects. What are they?
If in the same molecule you have a more electronegative atom, it's going to pull the electron density towards it.
So the more electronegative atoms you have, you start to pull electron density towards them. What do we know about inductive effects, though? How do they work? Remember we said they work like the telephone game, right? And what do we know about the telephone game? If I tell Abby something, that I guess since everyone's gone almost, it doesn't work quite as well, right? So imagine we actually had a classroom that was full, right? But if I tell Abby something, she's going to tell that to Morgan, right? She's going to tell that to Darren, and then she's going to tell it to the 30 other imaginary people that are here. Right? By the time it gets to the last person, is the message going to be the same? No. Are parts of the message going to be still valid? Sure, probably, right? But the point being what? The further away that my negative atoms are, right, the less of an inductive effect they have, right? You guys remember that? Did we talk about that? This book talked about that. Yeah. Okay. So what does it say? Resonance, inductive, atomic size, electronegativity, and
In geometry? For the
geometry related back to, begins with an H.
hybridization.
Hybridization, right? So hybridization has another effect with this also, right? Where did we learn all of that stuff? The acid-base chapter, right? that still important? Do all of those apply to how we stabilize a carbocation? Yes. Got it? Cool. So, understanding everything about everything now. You guys can start working those I'm putting them up here. All right. Have at it. While I enjoy my bribe from my more favorite class, who brings me bribes. I know. You should have. Too late now, Freddie. This is the secret, because as I've told you guys before, like I get super hungry all of a sudden when I get to your guys' class, so I have to bring my Dr. H snacks. All right, so let's bring it together here for just a quick second. Up at the top, what do we got? First reaction. All right, build your case. Convince me. What do we see? Go ahead.
So, first thing, kind of looking at the solvent, it's not bulky. It's not a bulky
Okay, so we got water in there. It's not a particularly bulky substrate or reactant or solvent. Okay. What else?
It's a weak nucleophile.
Water is a weak nucleophile. That's important. What else?
Why is it a weak nucleophile?
Why? Why is it a weak nucleophile? Dr. H, that's because in the book it gives a table, and the table told me that it is. Therefore, it is a weak nucleophile. Okay, what's a nucleophile?
Something that wants to go out positive.
Something that files some nukes, right? What's in the nucleus? Positive charges, right? Protons. And what does it mean to file something? P-H-I-L-E. To like it, right? To love it. So if you want to file some nukes, you really love positive charges. Okay? What loves positive charges? Negative charges, right? So what makes something a good nucleophile? Something with a negative charge. Does this have a negative charge? It has a partial negative. So, is it a good nucleophile? No. Can it act like a nucleophile? Yes. But is it particularly good at it? No. So I call it a weak nucleophile, right? Good? Okay. So not a bulky solvent. Weak nucleophile. What else? Darian, give me something. What do you notice?
You could make a carbocation
Okay, what do you mean?
when you lose the leaving group.
So back that thought up for just a second. So the leaving group is what flavor?
Secondary.
Secondary, okay? We've got a secondary leaving group. We could make a carbocation, right? Okay, Morgan, give me something else.
You could have a hydrogen bonding from the hydrogen on the water.
Okay, so our solvent could have hydrogen bonding, which classifies it as what kind of solvent?
Polar
A polar proton, okay? That's important too. Got it? You know who's next? It's Kate, all right. I'm just kidding. No. Tell me, Abby, what do we got? What else do you see?
just
Bromine's
bromine's a good leaving group.
a good leaving group, okay? All right, Kate, now it's your turn. What else?
The water a weak base as well.
Water could be a weak base as well. Good. All right, Catherine. The further along, the harder it gets, right? Man, everyone already took all the good answers. What else can we see?
I don't know, that's all I thought of.
Okay. Well, there's something to help Catherine out with. What else do we notice? Yeah.
So the molecule itself on the beta position is sterically hindered.
The carbon next door to the leaving group, what do we notice? quaternary carbon, right? Pretty darn bulky. Okay. What else? Now we're getting into some of the very, say, maybe obscure stuff that we haven't talked about too much yet. Something important. What temperature is this reaction run at? Maybe, right? We didn't specify it, so we assume it's run at a lower temperature. Why is that important?
It's run at a lower temperature, we said that it favored, the acid
The
reactions.
substitutions, right? Good. Temperature. Gotta check for that. Sterics. We gotta, like Darren had said there, right? We gotta look at what the leaving group is. Is it secondary? Okay? Like Sophia said, we also gotta start to look next door. Okay? We also gotta look at the solvent, or whatever substrate is with it. Is it a bulky? Is it non-bulky? Okay? We gotta look whether it's a polar protic solvent or polar aprotic. Can it form hydrogen bonds? What does that do? Is it a good leaving group or not? Can it act like a nucleophile? Can it act like a base? Right? Yeah. Do I expect you guys to be able to do all that? Yes. Why? Why am I torturing you guys like so? Because I am a spiteful human being, and I need to share my negativity with everyone, right? What am I really asking you guys to do? I'm asking you guys to pay attention, okay? I'm really getting you guys to look at the important parts of chemistry. Finding your positives, finding your negatives, finding the electronics, finding the sterics, and making an argument based off of that, okay? So all that evidence that we just said, what does that point towards? Likely we're going to do what? Hmm?
E2.
E2. Those are kind of on the opposite ends of the spectrum there, right? We got E2 on one end, we got SN1 on the other end there, huh? Okay, well, what do we need for an E2 to happen?
Hydrogen that is 180 degrees from the leaving group.
Okay, we need a hydrogen next door to the leaving group. Well, we do have that satisfied. Okay, that's good. What else needs to be around for an E2 to happen? Hmm?
We actually need a strong base.
A strong base. Do we have a strong base here? Certainly not. Right? Certainly not. We do have a weak base though, right? So we got a weak base, weak nucleophile, secondary leaving group, quaternary carbon next door, polar protic solvent, low temperature. What's that all kind of pointing towards? A fight between which two? Probably what? SN1 and E1, right? Could SN2 happen here? Might. Be pretty darn slow, right? We got that butyl, that tertiary butyl group next door to it, right? That'd be slowing things down for sure. Okay, so our current argument is SN1 and E1. So give me the products for them. favorite thing in the world, which is to loom and judge horses. Remember, every time, right? Every time we have a carbocation. Yes, but what consequences? No, you're fine. I like it. I'm just trying to get you to think of every time you generate a carbocation, you know, you go look what? Next door, right? And look for what? Shifts, rearrangements, right? Don't forget. Be careful, be very, very careful. Oh man, that was I need a big X stamp. Right? Good. Okay. Looks like you're on the right stuff though. Oh, okay, I see what your methyl group became small in stature.
Yeah.
Alright, we got it. Alright, let's give myself some space. Alright, how do we start the mechanism for an SN1 or E1?
Rolling up leaves.
Okay. It's off to quarantine. So topical humor. I'm so with it. If I can follow this, that'd be useful. Okay. All right, carbocations. Woo! I think I caught far too many of you guys with this. Every time we generate a carbocation, what should we always do? Always. Stop, look next door and what?
Report like if it's tertiary,
Look next door for secondary, tertiary, primary, see if we can rearrange or shift to get to a more stable position. When do you do it? Always. I'm sorry, let me rephrase this. Always do it unless you're on an exam or a quiz. Then don't do it, okay? Don't. Because I've got these, I told you guys about my sparkly pens, right? I got a purple pen with glitter in it. Ugh. I can't wait to use it. I'm joking. I told you guys, I don't, you know how hard it is to grade exams where you guys get stuff wrong? It takes forever. I just want to do the fun parts of the job. I really, as much as I joke with you guys about it, I don't like to take points off of people's exams. And I'm telling you exactly where you guys are going to miss points on this next exam. Some of you guys are going to do this. You're going to make a carbocation, and you're going to be happy and just move on. Right? And I know exam's stressful, and there's a lot to remember. I got it, I promise. Promise. That's what I'm trying to get you guys in the habit now, right? Just like you guys are in the habit of wearing, you get up, You do what you need to in your morning routine, and before you get out the door, what do? Yep, I've got pants on, okay? You guys are in the habit of making sure you're wearing the appropriate clothing before you step out, right? Do you guys have to think about this even? Or is it just a habit? Depends on the day. All right, Freddie. I'll be looking around. Oh, it's Saturday. Freddie's not wearing pants. Oh. Right? Do you guys get the point I'm making, though? You have to develop the good habits. I know, and this is what I mean with you guys are fighting me on this stuff. Just do it. Or don't, right? Always stop to look. Yep. So we look next door. Right? We look next door, we see a quaternary carbon. Oh, I'm sorry, I drew that wrong. It should go like this. There we go, right? What? No.
Can't draw an arrow from the positive.
You draw an arrow from a positive. Okay. So we do methyl shift. Where's my positive charge?
No.
Hmm? On the pink, right? Positive charge is from where you took the bond, right? Does it really matter in this case? No, that's symmetrical. Is it always going to be symmetrical? No. And then is it important to recognize where your positive charge is? Yes. Dr. H, I don't have colored pens. Number it, okay? Number it 1 and 2, number it A and B, right? Well, not number A and B, right? Right? Label it A and B, I don't care, call it Steve and George or whatever you want, right? Pay attention to where your carbocation ends up, okay? All right, so now we've done our shift. Now we can take our 2 paths, right? We'll do red and black. I guess we'll have to do the red ones because that's going to take up less space here. So I kind of trapped myself. If we do this, we can do this, and we can do this. I like it. Oops, I don't like that. Okay. Huh?
That's the E one right there?
Yep. I thought you said that's evil. I'm like, I don't know. I can't judge its intent, but right? If we follow the black. Okay, and we're done, right? Class is stressful. No. Oh, crap. What did I get wrong now? Jeez, you guys are so picky. What's wrong with this?
There's a positive on the.
Exactly. Don't forget, don't forget your formal charges, okay? You see 3 bonds to an oxygen, positive formal charge. All right. How long did it take us to work through one problem? Why is that? Is there a lot to go through? Yes. Is there a lot to think about? Yes. Is it because I'm talking slowly? Yes. As I'm trying to fill time like, geez, I don't know, I gotta stand here for an hour. Gotta tell more jokes. How many ducks does it take to know? Right. Why am I spending all this time? Just because this is what I want you guys to do. So I want you guys to be the little ducklings and I be the mother duck. And you guys are following through exactly what I'm doing. I spend a lot of time analyzing, you spend a lot of time building a case, then you put pen to paper to start drawing something, okay? And at the end of it, what happens? We have a beautiful story to tell. There are my two mechanisms, right? They're nice, they're pretty, we didn't make any mistakes. One more thing to think about, which one of our mechanisms is likely our major product?
U1.
Probably our SN1 in this case, maybe, right? Now, I'm not saying Sophia's wrong either. Why is it always tough to tell with SN1 and E1?
Because they both have the same rate determining step.
Right? They both have the same rate determining step. What is the rate determining step responsible for determining? I'm gonna go with the rate, right? You guys with me on this one? The rate determining step determines the rate. The rate of what? Either of these reactions, both of these reactions, right? Now, the contrivance that we kind of have in this class is that because we said room temperature or low temperature, we might say that SN1 is favored, right? But in reality, if you form one product, you're probably going to be forming the other one too, right? There's other ways we could start to push the equilibrium in one direction versus the other, okay? You guys with me on this though? Likely both are going to form. Make sure you guys can draw both mechanisms. Make sure you guys can identify the products. Make sure you guys can build your case, that kind of stuff. Yeah.
So these two would be the major products, but
Yeah.
there would be minor products?
Yes, there would, yeah. The minor products would maybe come from something like an E2, right? E2 would be very, very slow in this case, right? You just don't have a good base, right? You know, but it could, maybe, right? It could, right? SN2 would be really, really slow, right? You know, you got that bulk next door there, but it could happen also, right?
Okay.
You could get some minor product before the rearrangement, right? So you could get some stuff from there too, right? It certainly won't be clean, right? There will be just, this is the one product. There's gonna be a lot of mess in there. But these are going to be your major products. Cool.
So,
Yeah.
so on an exam,
Yep.
would you ever ask us to provide like the minor products, or is it always?
Yeah, I
the
could,
major?
right? Then it takes like 4 hours to answer one question. Right? But yeah, certainly could. All right, yes.
Does the time it takes to form the pi bond have an effect?
Ah, fantastic question. What do you see?
Chemical shift.
How many steps does it take to get to my product in red after the formation of the cation?
2.
One, right?
One.
Right? For here, it takes 1 step. How many steps does it take here? 2, right? We have to right? The OH attacks end this, right? You guys with me on this? It's a great observation. What's easier to do, take 1 step or 2? One, right? So do you guys see where we start to even kind of mix this up a little bit more? Right? The rate determining step determines the rate, but if we have 1 or 2 steps afterwards, right? Then we have to take that into account also, which means what? Things get complicated, right? But you're absolutely correct. So we just kind of, but it is a good observation, right? That's why I can't really 100%, well, that's not necessarily true. There's very rare cases where we 100% do SN1. We have to put it in special conditions where we can't do an elimination, right? It can happen, but we have to kind of build the molecule around it in a certain way. Okay. Question 2. let's see, I think we ended with Freddie last time. Right? Okay. All right, Alana.
This is a good meeting group.
We do have a good leaving group. Let me build upon it. Let me ask you a question to build upon it. What flavor of leaving group is it? Hmm?
Flavor?
Yeah, primary, secondary, tertiary.
So. Secondary.
Secondary, good. Secondary, good leaving group. All right, Sophia, what else?
It's a strong base.
Strong base, how do we know?
Because the charge is localized.
Okay, we got a localized negative charge. Okay? Ian, what do we see?
It's also a good nucleophile.
It's also a good nucleophile, right? How do we know it's a good nucleophile?
It has a
Yeah, we look for something with a negative charge, right? That usually indicates a good nucleophile, right? Jose, what else?
We have these oils next door.
You have what next door?
Hydrogens.
Okay, we've got a hydrogen next door to our leaving group. Okay. All right. Small class, so I have to ask each of you guys a lot of questions, right? Darian, what else?
There's no steric hindrance for leaving groupings.
Say that one more time.
There's no steric hindrance for leaving groupings.
Where the leaving group is, there is some, right? It's a secondary, right? But what about next door?
There's steric hindrance.
Right, we've got some steric hindrance that's next door. They've got that big bulky T-butyl group, right? Morgan, what else?
The solvents polar inverted.
Right, we have a polar protic solvent, right? We've got an OH, or alcohols are polar protic, right? I didn't call on you yet. What if I was going to skip you? Justin, no, just kidding. Go ahead, Abby. Hmm?
This is harder when someone's gone.
Yeah. So what are some of the things we looked for in the last problem?
Hybridization. I don't know.
It is secondary, right? The leaving group secondary, that's good, right? So we talked about sterics on the leaving group. Where else should we look for sterics?
Isn't it a bulky, like the oxygen?
So this would be a non-bulky base, right? We have a primary oxygen with a negative charge, right? So a non-bulky base. We really only know two bulky bases so far, okay? So we have a non-bulky base, a non-bulky nucleophile. All right, Kate, what else?
I guess the hydrogen bonding of the solvent goes with it being polar.
Polar protic, yeah. Really only about one more thing that I can think of. And it's the last thing we talked about on the last problem also.
Would it form a terminal alkene?
It might, we'll get there yet, right? We'll get there, but before we put pen to paper to see what the product's gonna be, we're still building evidence for our reactions. So remember the last thing we talked about was temperature, right? So we didn't specify temperature here, we'll assume it's at room temperature, okay? But always something to pay attention to also, right? Man, we almost made it around the whole room on this time, right? Is that a lot of information we gathered? Is every bit of information that you guys gathered important? Yes. Okay? So what does that all add up to? We've got a secondary leaving group. It's got some steric hindrance next door. We've got a strong base, a strong nucleophile that's unhindered. We're at room temperature, polar protic solvent, right? What are we all kind of pointing towards here? Probably E2, right? In fact, E2 is going to be favored here, okay? Now, remember, as I forget who said it, I think maybe Jose said, right? Next door to our leaving group, we have a hydrogen, okay? How many hydrogens are next door? 3, but they're all at one place, right? Do you guys get why that's important to look at? Because if we had multiple hydrogens next door, we have to say which one would lead to the Zaitsev or the Hoffman, the more or the less substituted alkene. Got it? Okay, so what's our product here then, or what's the dominant mechanism? E2 leading to what?
Locate the hydrogen that's 180 degrees.
Yeah. So in this case, we fortunately don't have to do that, right? Because we have those 3 hydrogens there. We can just assume rotation until it hits the right one, right? It's not going to change anything. Everyone's favorite. Good old buddy, Mr. E2. Nice, easy, to the point. What's unusual about this product though?
It's a monosubstitute.
Yeah, right? Make our monosubstitute alkene. Does it have a choice though? No, right? No. Don't have a choice. It's not like we can rearrange and make a hydrogens in a better place. To rearrange, what do we have to generate? A carbocation. Listen, this is important. Are you ever going to generate a carbocation? Are you ever going to have a full positive if you have a full negative around? No, you will not. Okay? If you have if you're going to generate a cation, make sure you don't have any negatives around. Okay? Don't do it. It'll become more and more evident as we go through more reactions, especially as we get to the second semester. Don't make negatives if there's positives around. Don't make positives if there's negatives around. They're going to react way too fast. Right? Way too fast. Reminds you of your email. I don't know. You asked me when the class is. Right? Wasn't it you emailed me about who had somebody in here?
Oh, I did.
Yeah.
I couldn't remember.
I forgot to email you back and say I'm sorry. I have no idea. I don't even know what I'm teaching. So I thank you for telling me what I'm teaching next semester.
They're listed already apparently, because of athletes, like we're allowed to register early.
Sure.
I have them all listed.
Oh,
So when
okay.
I started adding them to my cart, it said you were teaching it.
Oh, cool.
So that's how I was like, okay. Yeah, it says like just 12 to 12:01 to be determined. That's like, well.
I really don't know. That'd be a Dr. B question. He's the one who kind of puts that stuff together. Usually it's probably going to be like the 9 a.m. block is usually where they end up putting this stuff.
Okay.
But I can't 100% tell you. I have zero control over that. Otherwise I'd make it a 5 a.m. class. Get the day going, get the day done, right? What? What? You have the rest of the day to yourself, right? That's my view on these things, right? Get it done. What? Just think about it. You'd be done with classes by 7 a.m.
Yeah.
Then you could go to the beach for the rest of the day. Well, you guys all have to like go work out for the rest of the day or something. Right? Wouldn't that be great though, to have all that free time? Anyway. All right, no, I can tell I didn't convince you guys, okay. All right. What might be some minor products here? Probably only our SN2, right? Why? Because if you do SN1 or E1, you're going to generate a carbocation, and that's really not going to happen if you've got a negative charge around, okay? Yeah?
Is it also because you have a good nucleophile and a strong base?
Yes, yeah, yeah. But why would the SN2 be slow? Why would it be the minor product in this case? Give me 2 observations, I guess. Yeah.
The hydrogen, next to the leading group stays contained.
The hydrogen next to the leaving group is there. How does that affect an SN2 reaction?
Because it has to push through all of the hydrogens.
It has to push through everything,
Yeah.
right? So next door, what I will say is the carbon, right, the carbon next door to the leaving group there is very sterically hindered. That's going to certainly slow it down. And the leaving group is what? Secondary. That's going to slow it down also, right? All right. But hopefully at this point, I just want to kind of wrap this up. Tie a nice bow on my thoughts here, right? So, good leaving group, secondary leaving group, lots of sterics next door. Oh, I put 2 negatives there. Sorry, that's a little typo on my end. Hopefully you guys caught that. I think that should have been sorry. Polar protic solvent. We assume room temperature. We have a powerful base. A crappy nucleophile. Uh-oh. Well, I should back up my words here for just a second. Not as good a nucleophile as we might expect. But Dr. H, I hear you say, it has a negative charge. And as you've taught us in organic chemistry is black and white. Therefore, if negative charge, good nucleophile. Right? Okay. So hang on to that thought. But we do have a powerful base. We've got a hydrogen next door to our leaving group. It's a secondary leaving group. It's a good leaving group. There's sterics. It's low temperature. Blah, 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 blah. Right? All that stuff that we walked through the room twice with on the previous problems. Do I expect you guys to be able to do that for this problem? Yes. Would it be good practice to go do that? Yeah. Yes. And all of that would point us towards an E2 in this case also, right? In fact, it would be even more prone to be doing an E2 in this case. Why? Because of sterics, okay? Sterics slow down SN2 reactions. Could our previous example have done an SN2? Yes. Will this one do an SN2? No. Okay. Because our O with a minus charge is extremely sterically hindered. Okay. Very, very, very rarely is this going to act as a nucleophile. It's going to far more frequently act as a base. Yep.
So within SN2, is it, so when you're saying it's like sterically hindered, is that because the molecule itself is sterically hindered and
Yes.
the,
When we're talking about sterics, I'm looking at both parts of this. Where the leaving group is and what's next door, and where the minus is and what's next door.
okay, so because this is way more sterically hindered,
Yep.
it wouldn't even generate, while the last one wasn't.
Well, the last one wasn't as much, right? It's all a relative here, right?
Yeah.
I'm not saying the last one was fast. I'm just saying it would be faster than this, right? Good. So if we do this again, we end up at the exact same product that we had before, which is that guy there, right? Alrighty. Seems like a good place to pause it for the day. And give you guys back your exams.